Hi guys, welcome to homework number 20. I will be sharing this right now so we can go through this homework immediately. So we have the problems in the slide here. The very first problem is focused on concept question 11. And it says the drawing shows edge-on views of 3 parallel plate capacitors with the same separation between the plates. The potential of each plate is indicated above it. Rank the capacitors as to the magnitude of electric field inside them. So since they have the same separation, so all you need to check is to see the potential difference between the plates, the parallel plates. So electric field is proportional to potential. So if the potential difference is large, the electric field will be large. So you can see C has the highest potential difference because it's this plate minus this plate. So it's 50 minus 250. That's 50 plus 250. That's 300 volts. Then followed by B. So let's see what B has. 150 minus 100. That's 150 plus 100, 250 volts. So 300 is greater than 250. And then we'll have 250 minus 50. So that just gives us 200. So we'll have 300, 250, 200. So it's C followed by B, followed by A. C is the biggest, followed by B, followed by A. So that's the ranking, largest to smallest. So you just need to know the electric field is proportional to the potential. Okay. The next problem is focused on concept question 16. It says a parallel plate capacitor is connected to a battery that maintains a constant potential difference between the plates. If the plates are pulled away from each other, increasing their separation, what happens to the amount of charge on the plate? So let's look at this formula. So capacitance has two formula. The first one is A epsilon naught over D. So when we increase D, A decreases, C decreases, the capacitance decreases. So we go to another formula of capacitance. Charge is capacitance times voltage. Voltage is charge over capacitance. So you see, if we're making the potential constant, the V constant, and we are increasing D, it means we are making C small. If we're making C small, what are we going to do to Q to keep V constant? So if I'm changing C, I have to change Q the same way. If I increase C, I have to increase Q to keep V constant. But now by increasing D, I am decreasing C. So if I'm decreasing C, I have to decrease Q to make V constant. So the amount of the charge decreases because the capacitance decreases. That is the only way we can make the potential difference between the plates constant. Okay, next problem. It says the inner and outer surfaces of a cell membrane carry a negative and positive charge respectively. Because of these charges, a potential difference of about 0.064 volts exists across the membrane. The thickness of the membrane is 7.2 times 10 to the negative 9 meters. What is the magnitude of the electric field in the membrane? So electric field is minus change in potential over the distance, the separation. So it's minus VB minus VA over delta S, but we want the magnitude only. So the minus is important if we're going to consider the direction of the electric field. But if we want only the magnitude, we can ignore that minus and just say minus VB minus VA is the same as VA minus VB. We just put the magnitude there, which is given to be 0.064 volts divided by the separation, and that gives us our electric field in magnitude. If they ask us for the direction, then we now have to go in details to find which one is negative surface, which one is positive surface, and the directions of the electric field from each. Okay. The next one, chapter 19, problem 35. It says a spark plug in an automobile engine consists of, let me silence this phone, excuse me. Okay, a spark plug in an automobile engine consists of 2 metal conductors that are separated by a distance of 0.98 millimeters. So we're going to convert that to meters. You can see here 0.98 times 10 to the power minus 3 meters. When an electric spark jumps between them, the magnitude of the electric field is given in volts per meter. So they're asking us to find the magnitude of the potential difference, which is E times delta S from the previous example. So the magnitude is just going to be E times delta S. So E could have been given to be negative, we'll put minus there, but E is given to be positive, so we'll just put a positive there. And we are given the magnitude. So, and this delta V, the change in potential difference, can just be gotten from here. 4.5 times 10 to the power 7 multiplied by the separation. And that gives us 4.4 times 10 to the 4 volts. Next problem, the drawing shows a set of equipotential surfaces in cross-section. That's chapter 19, problem 36. The grid lines are 2 centimeters apart. Determine the electric field at position D. So position D is between 550 volts and 450 volts. So here we're going to take the potential difference divided by the separation. So each box is 2 centimeters apart. How many boxes do we have between 550 and 450? 2 boxes, so that's 4 centimeters. So the potential difference divided by the separation is a magnitude of our electric field. Is that okay? So we're going to have 550 minus 450 divided by the separation, and we're going to get that as the electric field. Okay. Right here, you can observe in this problem the 4 is converted to meters. That's the times 10 to the minus 2 here. So it's 2 plus 2, 4 times 10 to the minus 2. The next problem is chapter 19, problem 39. It says the drawing shows the electric potential as a function of distance along the x-axis. Determine the magnitude of electric field in the region A to B, B to C, C to D. So electric field is change in V over change in X with a negative sign. Is that okay? So here we have change in V. The V is constant here. It doesn't change from A to B. So it stays from 5 to 5. So it's 5 minus 5 over change in X, 0.2 minus 0. It's because potential over X over distance. So basically it's like taking the slope. So this one has no slope, so it will have no electric field. And then the other one, electric field from B to C has, the minus doesn't matter. As you can see, they just want the magnitude, so you don't care about the sign. So here is the bottom one minus the top one, 3 minus 5 over 0.4 minus 0.2 for this one. And then this one is 1 minus 3 over 0.8 minus 0.4. You get that one. And that just gives you the electric field magnitude. Okay. Chapter 19, problem 42 is the next one. And it's saying, what is the capacitance of a capacitor that stores 3.3 microcoulomb of charge on its plate when its voltage is 6 volts applied between them? So we have charge is Q over V. So capacitance, we always confuse that with charge. You have to be careful. So C's capacitance is charge Q over V, the potential difference. So we have the charge and the potential difference, and we're asked to find the capacitance between them. So that's the capacitance. The next problem, chapter 19, problem 43 says the electric potential energy stored in the capacitor of a defibrillator is 75 joules and the capacitance is given. We're asked to find potential difference. So energy is half CV squared. C is capacitance, not charge. Is that okay? Okay. So we're asked to find V, the potential. So from here, if we make V subject of formula to be 2 times energy divided by C square root. And that gives us the potential. So we have the energy, 75 joules. We have the capacitance, 130 microfarad. So we'll put it there. Converting the micro to times 10 to the negative 6. And that gives us our voltage. Next problem. Chapter 19, problem 45. It says the electronic flash attachment for a camera contains a capacitor for storing the energy used to produce the flash. In one such unit, the potential difference between the plates of an 760 microfarad capacitor is 250 volts. Determine the energy. Energy is half CV squared, so it's half times capacitance times voltage squared. You get that in joules immediately. Then assuming the flash lasts for 6.7 milliseconds, find the effective power. So effective power is energy divided by time. We've gotten the energy divided by the time in milliseconds times 10 to the negative 3 seconds, and then we get the answer in assignment. Okay. So far, so good and easy. So we'll go to the next one. Focus on concept question 02. Say, which one of the following graphs correctly represent Ohm's law? So Ohm's law says V equals IR. So if I write that here, that voltage equals current times resistance. So it means voltage and current are directly proportional with resistance as a constant. So when I have a direct linear relation with no constant C, it means there is no y-intercept in my curve. So I'm going to have a straight curve from the origin that goes straight up, not straight down. Straight down is an inverse proportionality. So it's a direct proportionality. So I'm going to have straight up. As V increases, current increases with resistance as a constant. This is an inverse relationship. He's saying as V increases, as you're increasing V, current is decreasing. So this inverse relationship. And this one is a square relationship, so we don't have that. We don't have that here. So it's going to be, the correct answer is C. This is the direct proportional linear relationship between V and I. As V increases, I increases proportionally. Excuse me. With R as the constant. Okay. Next, the peak voltage of the AC current in a circuit is 6 amperes, and the peak value of the AC voltage applied to the circuit is 8.4 volts. What is the average power delivered to the circuit? So average power is the IRMS current times the VIRMS current. So the IRMS, which is root mean square, and the VRMS, root mean square, they are the peak current over root 2. I naught is the peak current over root 2, that's IRMS. VRMS is the peak voltage, V naught over root 2. So we are given the peak current and the peak voltage, so we're going to use this formula. We are not given the RMS current and RMS voltage. So we're going to put the peak current, peak voltage divided by root 2, divided by root 2. So peak current 6 amperes divided by root 2 times peak voltage 8.4 volts divided by root 2, and we'll solve this. Root 2 times root 2 is 2, this times that is that, and then we get our answer for the average power delivered. Okay, next problem. So the next problem says, a defibrillator is used during a heart attack to restore the heart to its normal beating pattern. A defibrillator passes 17 amperes of current through the torso of a person in 2.2 milliseconds. How much charge moves during this time? So charge over time is current. So charge is current times time. So this is the charge flow over the change in time within the charge flow, that's the current. So multiply the current by the time taken, we get the charge. How many electrons passes through this? So we'll know the number of charges divided by the electronic charge. We know how many electrons are in that charge. One electron has this charge. How many of these charges are in this charge? It gives us the number right here. Okay. Next is chapter 20, problem 03. It says a battery charger is connected to a dead battery and delivers a current of 4.6 amperes for 4.7 hours, keeping the voltage across the battery terminals at 12 volts in the process. How much energy is delivered to the battery? So the charge is current times time. So we get the current first of all. So after getting this charge, the charge from current times time, we convert the time to seconds. And then energy is charge times the energy, the voltage. Is that okay? So we have it says the energy here, the charge we have here times the voltage is going to give us this joules. So the charge times the volts is the energy. Okay. Where do I have that here? Yeah. So because they are asking 0.934 times 10 to the 6 joules, that becomes the energy. Yep. Okay. Next, another way of calculating energy is just current times voltage times time. Is that okay? So it's current times voltage times time. So if we do that here, the current times the voltage times time, we are doing the current times time to get delta Q basically. So if you want to just bypass this delta Q stage, instead of saying charge times voltage, it's current times voltage times time. That is how we define energy. So it's power times time. Current times voltage, IV by itself is power, times time is current. So it's the same thing, just using the charge notation. Okay, next, chapter 20, problem 005, go. Suppose that the resistance between the walls of a biological cell is 6.1 times 10 to the 9 ohms. What is the current when the potential difference between the walls is 83 millivolts? If the current is composed of sodium ions, the positive charge equals the positive electronic charge. How many such ions flow in 0.54 seconds? So the first point is to get the current, which is voltage over resistance from Ohm's law. We get that. Then the number of sodium ions is to get the number of charge divided by an electronic charge. So current times time is the charge that's flowing. The time times the current we just got will give us how many charges have flown divided by one electronic charge to get the total number of charges. Is that okay? Or the total number of sodium ions, which is the electronic charge inside the atom, charges that are flowing. Okay, if you take that down, The next problem, chapter 20, problem 16 says high voltage power lines are familiar sight throughout the country. The aluminum resistivity that wire used for some of these lines has a cross-sectional area that. What is the resistance of 12 kilometers of this wire? So resistance is resistivity times length over area. Resistivity is given, length is given, area is given, all in SI units, and you just get your answer. That's the resistance in ohms. Okay. Two more problems. Chapter 20, problem 23, excuse me. Says the heating element in an iron has a resistance 20 ohms. The iron is plugged into a 120 volt outlet. What is the power dissipated by the iron? So power is current times voltage. Is that okay? But another formula for power is voltage squared over resistance, because current is voltage over resistance. So it's voltage over resistance times voltage. So that's why you have voltage squared over resistance as power. So it's going to be 120 squared over 20. So you're not giving current. So you're going to find current in terms of voltage over resistance from Ohm's law and multiply that by voltage. Okay. And then the last problem says the RMS current in a copy machine is 7.67 amperes. And the resistance of the machine is that. What are the average power and the peak power? So average power is the square of RMS current times resistance. So it's current times resistance. So I times IR. I mean current times voltage. So it's I times IR. So it becomes I squared times R. Okay. So you're putting the voltage as IR. So IRMS times IRMS-R, that's I squared R to get your average power. And then the peak power is just twice the average power. And we're done with this. So I'll see you guys next week. Have a good one.